I have a question for you. When you get in your car and, turn the key, are you 100% sure the engine is going to start?
100%. Oh, no, not at all. I mean, the battery could be dead, the starter could be shot, maybe a rat chewed through a wire or something.
Right.
I'm pretty confident, sure, but I'm not certain. Never certain.
Exactly. You're betting. You're operating on a high probability. But in the world of classical computer science, the code that runs your bank account or your calculator, that kind of ambiguity is the enemy.
Oh, absolutely. Things are true or they are false. 1 or 0.
It's binary. And that works great for spreadsheets.
For spreadsheets, yeah. But it is absolutely terrible for survival in the real world.
Because the real world is messy. It's just noisy, sensors get smudged, people lie, and sometimes things just happen for no reason at all.
Right. So today on the deep dive, we are looking at how artificial intelligence learned to stop worrying and love the uncertainty.
We are unpacking a really dense but fascinating chapter on probabilistic reasoning.
And this is really the story of how AI moved from that rigid, brittle logic to systems that can actually function in chaos. And we're going to be talking about the tool that really changed the game, the Bayesian network.
And we aren't just skimming the surface here. We're going to look at the architecture of these networks, why trying to do the math perfectly is, well, it's actually impossible even for a supercomputer.
It really is.
And then how modern systems handle things like identity uncertainty, where the AI doesn't even know if the thing it's looking at is even real.
It gets surprisingly philosophical by the end.
So let's start with the mission. Why can't we just give a robot a list of rules? The old Asimov approach. If you see a red light, stop.
You can try. I mean, that's what we did in the 80s. But here's the problem. What counts as a red light? What if the sun is glaring off the lens and the camera is only, say, 60% sure it's red?
What if the person is just a cardboard cutout?
Right. If the robot only thinks in true or false, it freezes, it crashes.
Can't make a judgment call.
Exactly. It needs to be able to say, there's a 90% chance that is a red light, so I should probably stop just in case. It needs to weigh the risks.
It needs probabilistic reasoning.
And to do that, you need a map of the world.
Which brings us to the Bayesian network, also known as a belief network or a causal network. So visually, what are we looking at here?
Okay, so imagine a whiteboard. You draw a bunch of circles on it. We call these nodes.
Okay.
Each node is a variable, something that can change. Like, is it raining or do I have a toothache?
Is the battery dead?
Exactly.
Yeah.
So you've got your circles. Now you draw arrows connecting them. These are the links. And usually that arrow represents cause and effect.
So you draw an arrow from cavity to toothache.
Right. The cavity causes the pain.
Simple enough, but how does drawing a few circles and arrows save us from all this chaos? It feels a little like we're just doodling.
The magic isn't in the arrows you draw. It's in the arrows you don't draw.
Okay, explain that.
So it's this concept called conditional independence. And it is, I think, the single most important idea in this entire deep dive.
Okay.
In the old days, if you wanted to model a world with, let's say, 30 variables, you tried to create a full joint distribution. You had to calculate how every single thing affected every other thing, all at once.
That sounds like an astronomical amount of math.
It's explosive. For just 30 variables, you would need to store over 1 billion numbers. 1 billion. It grows exponentially. You add one more variable, the whole thing doubles.
It's completely unworkable.
It's computationally impossible to run that in real time. But with the Bayesian network,
You just don't draw the arrow.
you look at the map and you say, wait, does the price of tea in China actually affect whether my car starts? No, then don't draw an arrow. And by explicitly stating what doesn't matter, you reduce that billion numbers down to maybe 900.
You turn an impossible problem into a manageable one. Let's ground this, because the source material uses this one specific example that I think really makes this click. The burglar alarm scenario.
The classic textbook example, yeah.
So picture this. You live in a house in Los Angeles. You have a burglar alarm. And this alarm can be triggered by two things. An actual
Burglary or a minor earthquake.
Right. So both of those are parents in our graph. They both point an arrow at the alarm node.
Correct. They both cause the alarm to go off.
Right. Now, you're at work. You have two neighbors, John and Mary, who promise to call you if they hear it ringing. So we draw arrows from the alarm node to John calls and Mary calls.
Makes sense.
Now, here is the test. Does the burglary node point directly to John calls?
Yeah. And that is the key. John isn't psychic. He doesn't see the burglar. He only hears the alarm.
So if I already know the alarm is ringing,
Then knowing about the burglary gives you no extra information about whether John will call. John is conditionally independent of the burglary, given the alarm.
the alarm acts as a shield. It blocks the information flow.
It's the perfect way to put it. And that blocking is what saves the computer a billion calculations. It lets us treat the world as a collection of local neighborhoods instead of one giant, tangled mess.
Okay, so we've built the map. We have our probabilities. We know John is a bit jumpy. He might mistake the phone ringing for the alarm.
And Mary listens to loud rock music, so she might miss it entirely.
We have the data. Now we need to use it. This is what the text calls inference.
Which is just a fancy word for asking the map a question.
Yeah.
You have evidence, John called, and you have a query. So, is there a burglar?
And how does the computer figure that out?
Well, there's the hard way, and then there's the good enough way. The hard way is called exact inference.
Right.
And one method is enumeration.
Which sounds like just counting.
It pretty much is. It's brute force. The computer essentially imagines every possible universe where John calls. In some of those, there's a burglar. In others, there's an earthquake. In a few, John is just, hallucinating.
And it just adds up the probabilities of all those universes.
To give you one exact answer, yes.
But didn't we just say that calculating every universe is impossible for big networks?
It is. Enumeration is incredibly slow. So, some smart researchers came up with variable elimination.
This sounded a bit like Marie Kondo for math when I was reading it.
It's not a bad analogy. It's about pruning. Suppose you want to know if there's a burglary, and you know John called. The algorithm looks at the map, and it sees Mary.
Right.
And it asks, do I have any evidence about Mary?
And no, we don't. We don't know if she called or not.
Then the math can actually sum her out. It proves that Mary is totally irrelevant to this specific calculation and just deletes her entire branch from the equation.
So it simplifies the map on the fly. That sounds incredibly efficient.
It is better, definitely better. But here's the reality check. Exact inference, even with these pruning tricks, is what computer scientists call NP-hard.
Which means?
It means that if your network gets complicated enough, specifically if it has loops, where A affects B, B affects C, and then C loops back to affect A, the calculation time explodes all over again.
It can grind a supercomputer to a halt.
Totally.
So we have this beautiful map, but we can't always do the math perfectly. What do?
We cheat.
We cheat.
We approximate. We stop trying to get the exact answer to the 10th decimal place, and we start simulating. This brings us to approximate inference.
And this is where we start rolling dice. The Monte Carlo algorithms.
Exactly.
Yeah.
Named after the famous casino, because that's basically what the AI does. It starts flipping weighted coins to simulate the world over and over.
So walk me through direct sampling.
Okay. Say you want to know if it's raining. The computer looks at the cloudy node first. It says, okay, 50% chance of clouds. It flips a coin. Heads. Okay, it's cloudy in this simulation.
So now we have a cloudy world.
Right. Then it looks at the rain node. Since it's cloudy, maybe now there's an 80% chance of rain. It flips another weighted coin. Heads again. It's raining. It just goes down the line like that.
And it does this, what, a million times?
Millions of times. And then it just counts. Out of a million simulated days, how many times was the grass wet? And that percentage is your approximate answer.
But there's a catch, right? The text mentions rejection sampling.
Yes. So suppose you have evidence. You know for a fact the sprinkler's on. You only want to simulate worlds where the sprinkler's on.
Okay.
But if the sprinkler's rarely on, maybe only 1 in 100 times.
Oh. Then 99 of my 100 simulations are going to be useless. I have to just throw them away because they don't match reality.
Exactly. You are rejecting the samples. It's terribly inefficient. You're just burning electricity to simulate worlds that you know don't exist.
So how do the pros do it?
They use the heavy hitter, MCMC. That stands for Markov Chain Monte Carlo, specifically an algorithm called Gibbs sampling.
This is the part of the chapter where the visuals got really interesting. How is this different from just starting from scratch every time?
So in the other methods, we built a new world from the ground up every single time. In MCMC, the system, it wanders. It starts with a complete state of the world. Maybe just a totally random guess. Burglary is true. Earthquake is false. Alarm is true. It just holds that state. Then it picks one variable, just one, say burglary.
Okay.
And it looks only at the immediate neighbors of burglary. and decides whether to flip that one switch from true to false.
It just flips one switch at a time.
Yes, it wanders through this state space, flipping one variable, then the next, then the next. And here's the key concept. When it decides whether to flip a node, it only looks at a very specific set of neighbors.
The Markov blanket.
The Markov blanket. It sounds cozy, right?
It does. What is it made of?
It's a shield of relevance. For any given node, its blanket is its parents, its children, and this is the tricky one, its children's other parents.
Great. Why the children's parents? My parents and my children I get, but why do I care about my kid's other parent?
Think about the burglar alarm again. The alarm is the child. You are the burglary node. The earthquake is the other parent.
Okay, with you so far.
If you know the alarm is ringing and I suddenly tell you there was an earthquake, the other parent, does that change how likely you think it is that there was a burglary?
Oh yeah, definitely. If there was an earthquake, that probably set off the alarm, so I don't need to worry about a burglar as much. The probability goes way down.
Exactly. The status of the other parent competes with you to explain the child. That's why they're in the blanket. The algorithm only looks at this tiny local neighborhood to make a decision.
So the AI is just wandering around flipping switches based only on these local interactions.
And the magic is, if you let it wander long enough, it settles into a kind of dynamic equilibrium. The amount of time it ends up spending in a particular state, say the burglary is true state, is exactly proportional to the actual probability of that event being true.
That is mind-bending. It turns a static math problem into a movement problem.
It's how we solve problems that are just too big for calculus. We simulate the wanderer.
Okay, I want to pivot a bit. We've been talking about these really rigid networks, burglar, alarm, neighbor, but the source material takes a hard left turn into relational and first-order models.
This is where we leave the toy problems behind, and we enter the real world of big data.
Because in the real world, we don't always know who the neighbors are, right? I mean, take Netflix. They don't have a fixed graph called user one and movie one.
No, they have millions of users and millions of movies, and that structure changes every single second.
Standard Bayes nets can't handle that.
No, they're propositional. They assume a fixed world. But for something like Netflix, you need relational probability models. You don't model John, you model a class of things called customer, and you define rules for that type of thing.
The text has a great example about book recommendations that explains this. It talks about honest versus dishonest customers.
This is a perfect demonstration of how these models handle nuance. So the model says, generally, a customer's rating depends on the book's quality.
Makes sense. Good book, good rating.
But the model can have a rule. If the customer type is dishonest, then that link is broken. The rating no longer depends on the book's quality. It's just noise or, manipulation.
It's called context-specific independence. The arrows in the graph can literally appear and disappear based on the data.
Right. And you can get even more granular. The text mentions the fan.
Oh, I definitely know this person.
Right. The model can learn that if an honest customer is also a fan of that author, they will always give 5 stars. So if fan is true, the rating also becomes independent of the book's actual quality.
So if a fan gives a book 5 stars, the AI learns, okay, I shouldn't really take this as strong evidence that the book itself is good. They just love the author.
Exactly. It's reasoning about the psychology of the user, not just crunching the numbers.
But then it gets even deeper. What if you don't even know what exists in the world? The notes mention open universe probability models.
This sounds like astrophysics, but it's really about the problem of identity.
Identity uncertainty.
Right. In a standard network, if I see user A and user B, I assume they are 2 different people.
Which is a reasonable assumption.
Not on the internet. It's not.
Yeah.
What if user A and user B are actually the same person?
Yeah.
Or think about intelligence analysis. You see a report about the jackal and another about J. Carlos. Is that 2 terrorists or 1 guy with a pseudonym?
If you get that wrong, your whole model is garbage.
Totally. This leads to the Sybil attack, which is a huge issue in online security.
That's the fake review problem, isn't it?
It's a reputation system nightmare. Suppose one bad actor creates 1,000 fake accounts to downvote a competitor's product. A standard AI looks at that and sees 1,000 separate nodes.
It sees 1,000 separate people who hate the product.
And it concludes, wow, this product must be terrible. Because it assumes that if there are 1,000 accounts, there must be 1,000 humans.
An open universe model is smarter.
Much smarter. It reasons about the existence of objects. It asks, what is more probable? That 1,000 distinct people all hated this product at the exact same time. or that there is one hidden object generating 1,000 signals,
It collapses the 1,000 fake nodes into one giant troll node.
which is a massive leap in intelligence. It's reasoning about the structure of reality itself, not just the attributes of things we already know exist.
Now, before we wrap up, I want to look backward a bit because probability wasn't always the winner here. The notes talk about the alternative approaches.
That's right.
Back in the 70s and 80s, AI researchers really tried to avoid all this. This gambling, they wanted rules.
They did. They loved expert systems. They tried to use certainty factors. They would code things like, if the sprinkler's on, then the grass is wet with a certainty of 0.9.
That sounds reasonable. Why did it fail so badly?
It fails because of something we touched on earlier, intercausal reasoning, or the better name, explaining away. This is the nail in the coffin for those old rule-based systems.
Okay, let's role play this so I can see the failure. I'm a rule-based AI.
Okay, observation 1. You look out the window, the grass is wet.
Okay, my rule says if rain, then wet grass. So since the grass is wet, my confidence in rain goes up a little.
Makes sense. Now, observation 2. You look a bit to the left and you see the sprinkler is on.
Okay.
In a human brain, or a Bayesian brain, what happens to your belief in rain?
It goes down. I don't need the rain to explain the wet grass anymore. The sprinkler explains it away perfectly.
Exactly. But the rule-based system struggles. It has a rule. Sprinkler on wet grass. And another rule. Wet grass rain.
Oh, I see the problem. Since I see the sprinkler, I'm even more sure the grass is wet. And since I'm more sure the grass is wet, my rule makes me more sure it rained.
Correct. You see the sprinkler and you think, wow, it must have stormed really hard. It just chains the logic forward. You can't look backward and say, oh, wait, the sprinkler makes the rain redundant.
That is a fatal flaw. It's the opposite of common sense.
It is. And that's really why Bayesian approaches eventually won. They capture that bidirectional flow of information. They understand that causes compete.
What about fuzzy logic? I feel like I hear that term thrown around. Is that the same thing?
Completely different beast. Fuzzy logic is often confused with probability, but they solve different problems. Fuzzy logic deals with vagueness, not uncertainty.
Give me an example.
Is Nate tall?
I'm 5'11".
Okay, so are you tall?
Sort of, I guess.
Exactly. It's vague. In fuzzy logic, we might say you are 0.6 tall. That is a fact about the definition of the word tall. There's no uncertainty there. We know your height.
Okay, versus probability.
Probability would be, is Nate a burglar? That is not vague. You either stole the jewels or you didn't. There's no 0.6 burglar. We just don't know the truth.
That is uncertainty. That is where probability lives.
One is about language, the other is about knowledge.
Got it. And finally, the text mentions Dempster-Shafer theory, which sounds very serious.
It deals with the distinction between uncertainty and ignorance.
The coin flip again.
Right. If I hand you a fair coin and ask the probability of heads, you say 50%. You're uncertain, but you know the physics of the system.
Sure.
Now, suppose I pull a mystery object from my pocket and keep my hand closed. I ask, what is the probability this object is heads?
I mean, I don't even know if it's a coin. It could be a button or a piece of lint.
Exactly. In standard probability, you're forced to assign a number. You might say 50% just to be neutral. But Dempster-Shafer allows the system to say, I have 0 belief in heads and 0 belief in tails. I am simply ignorant.
It creates a specific mathematical space for I have no idea what is going on.
Which is a really powerful idea.
It really feels like we've built this whole hierarchy of doubt from I'm 80% sure to I don't know if this user even exists to I don't even know if this is a coin.
And that is the triumph of this field. We figured out how to compute with doubt. As the mathematician Pierre Laplace said, and he said this way back in the 1800s, probability theory is nothing but common sense reduced to calculation.
It's not just counting dice, it's the machinery of thought.
It allows an AI to function in a world where we can never know everything. It weighs the evidence, it checks the Markov blanket, considers the priors, and makes the best possible bet.
Which leaves me with a final thought for you, the listener. If these Bayesian networks are the mathematically optimal way to reason, what does that make us?
That is the big question, isn't it?
When you decide to cross the street, or you get a bad vibe from a stranger, or you decide to trust a friend, are your neurons running a massive Monte Carlo simulation? Are we Bayesian engines?
Or are we just those sloppy rule-based systems from the 80s that just happen to get lucky most of the time?
The cognitive scientists are still fighting over that one.
Are we rational, or are we just full of useful heuristics?
I'll let you calculate the probability of that on your own. Thanks for joining us on the Deep Dive.
See you next time.